All right, good morning, folks. Welcome to your weekly Friday videos here on YouTube. When I said on Wednesday we would keep today relatively short, we will indeed keep today quite short. We'll keep it one video and probably to around the 10-minute point. What I encourage you to do over the weekend is to start studying if you haven't already for the exam. Make sure you're starting to look over the materials we discussed in class, and come Monday morning with any questions. We'll start off with a brief review of this after any questions have been addressed, and then we will have, of course, some time for discussing the weather, and then back to general circulation, which you see on the screen here as I start to chat. So when we talk about general circulation or global circulation, they're generally synonymous terms. What we're talking about here is what is the average flow in different parts of the globe. And so this is more of a large scale view. We have to, when looking at meteorology, address what's going on Earth on a number of different scales. We can't really understand, for instance, what's going on near Calais Christopher Hall or your dorm or your apartment until we understand Valpo, and we can't understand Valpo until we understand Indiana, and it kind of works on a number of different scales. And so here we're looking at this global scale. And here you're going to notice then that the local scale patterns actually effectively disappear. You're not going to see things such as flows off of Lake Michigan, or even something else that you might be used to near your hometown. And what this does is it helps us to identify what are the driving forces for the weather patterns. For instance, why here in the mid-latitudes, or I should even say near the middle of the United States, we typically see our weather patterns, our weather systems emerge from the west and move towards the east. Ultimately, this is still related back to the sun. Again, your 6 degrees of separation with the sun. The unequal eating of Earth's surface is critical for these patterns. We know that in the general sense, there is more sun near the equatorial regions than there are near the polar regions. And in many of these simplified models, you'll see that we really focus on that fact. Why do we care? Because it is going to help us to drill down to understand why the weather is in certain parts of the world. It's going to be the backbone for many of the things we work on going forward to help us break it into layers such as what's known as the mesoscale, things that are going to be affecting thunderstorm development, or maybe a land sea breeze if you're down visiting Mickey Mouse or even live in the state of Florida. And so we're going to start off with the simplest of the models, and that's what's known as the single cell model. Again, to be very clear up front, these are models. These are far from reality, but they get us closer to what is reality. They help us to understand what is reality. And so again, you're not going to look at the single cell model and say this resembles what weather looks like, because it doesn't. It is oversimplified. And so we assume a number of things. We assume that there's a uniform water surface. In other words, the entire Earth is covered in water. We assume that the sun is always directly over the equator. Don't get that conflated with what you need to know for exam 1 when we have established that the sun is directly over the equator on 2 days a year, those equinoxes. But the Earth still does have a tilt. And then even more crazy is the fact that we're going to assume that the Earth is not rotating. It's simply sitting there, sun over the equator, and covered in water. So, again, far from reality. But what we get when we set up this single cell model is a large cell known as the Hadley cell. We describe the Hadley cell as being thermally direct. In other words, we're going to have rising motion where we get substantial heating. Think of our terms such as convection. And we're going to get sinking motions in areas that it is cool. And so here, as you look at the single cell model, you can see that this is how things effectively evolve. Areas where the sun is directly overhead, the equator, we have hot conditions. Hot air is less dense and therefore will want to rise, and that lends to a low pressure. We're going to talk more about pressure systems moving forward. And so where that air near the equator that is hot is moving upward, this vacation of air from the surface, this motion of air from the surface upward, means that you're losing mass down by the surface. We see that there's a response to that with air trying to flow at the surface of this single cell Earth towards the equators. And what does that mean? It means that because there's less mass here, we ultimately end up with low pressure. This air rises up in our atmosphere until it becomes cooler. It then moves away towards the poles where we see sinking motion, cold air, more dense. And so we have this single cell, what is known as the Hadley cell. And so in this single cell example, we don't have, again, any rotation, so the flow is simply from high to low. This is going to be a theme that becomes very well established as we move towards forces and force balances shortly. Air, or mass, is always going to flow from high pressure towards low pressure. That's one of those things you can take to the bank in Met 103. It is always going to be true. And so on the right here, you see we'd have still equatorial tropical regions, subtropics, mid-latitudes, but notice how these are effectively exactly horizontal lines. We don't have any ebbing and flowing. It's exactly symmetrical about the equator, and that's because of all the constraints that we put in for our single cell model. But again, we have to keep it really basic to start so we can start to make things a little more complicated and therefore a little more realistic as we move forward. But again, keeping a couple things in mind moving forward that will be extremely helpful throughout the rest of the semester. This idea of warm air, less dense, rising. Conversely, cold air, more dense, sinking. This is going to continue and continue, especially as we move towards topics such as atmospheric stability, which is critical towards understanding thunderstorm development. So now we take a big change. This graphic right here is going to be very important. I will likely start off class on Monday with this diagram as a little bit of review, assuming you've watched the videos. And we'll continue to work on this as we get into lab next week, and we'll occasionally revisit it over the semester. And so in our 3-cell model, we initiate one substantial difference, which may seem small, but it's incredibly important. And that's that now we're going to allow Earth to rotate. Still covered in water, still got that heating directly over the equator, but now the Earth is spinning. And that introduces a lot more realism to what is going on. It allows that air that is warm to still want to move upward. Again, we're going to continue to have warm air less dense and want to rise, and cold air more dense and want to sink. But now we start to see some motions eastward and westward. It's still overly simplified. There is no land, because land, as we already have seen in some examples, really starts to complicate things due to the specific heat, changing ocean currents, so on and so forth. But what we see here is a number of new features. We still see these lows near the equatorial regions, and again, lows are going to be areas where we see rising motion. We see the air kind of coming together here in the northeast trade winds. And this is actually the southeast trade winds. This is a typo in the book. So again, southeast trade winds, northeast trade winds. But as these winds come together, we experience what's known as convergence. Air coming together. Think of if you converge on someone, you get closer to them. Not necessarily the best thing to do right now in the pandemic scenario. But the point being is that as you get this air coming together at the surface, it enhances that rising motion. And we even have an example here of where near areas of low pressure we may see storms in the tropics. We get equatorial lows, and then we have this additional feature now showing up called the Intertropical Convergence Zone, or the ITCZ. Intertropical, within the tropics, convergence, air coming together, and the ITCZ ends up being pretty important when we start to talk about a lot of the tropical rainfall and even the development of hurricanes and other tropical systems. However, as these trade winds move out this way, we also have a band called the westerlies, and you can see that we have air going kind of a northward direction here and a southward direction here, which means that it's spreading apart. This lends to an area around 30 degrees north, known as the subtropical highs. We see a term here called the horse latitudes. And the air is not coming together, so it's not converging, but rather diverging. Popular book series a while ago, if things are diverging apart, they're simply spreading apart. And so if air is spreading apart at the surface, as we see here in the cells, that lends towards sinking motion. Sinking motion is not going to be conducive to thunderstorms or cloud development. Generally speaking, it would lead to quiet or quiescent weather, clearer skies, and a lack of precipitation. You can see here between 30 and 60 north, dominated by what's known as the westerlies. This is the area that Valparaiso would be in, and I've talked about the westerlies on occasion to help highlight the type of weather we see here in this portion of the world. Polar front, again a low pressure dominant here as we separate the westerlies from the polar easterlies, again noting that convergence. Subpolar lows, again you're still getting to areas here that have substantially less sunshine in this 3-cell model, which focuses on the sun directly overhead at the equator. And so one other thing to note before I get into the cells on the left side of this Earth is that it is still relatively symmetric about the equator. We don't have land kind of throwing an extra wrench in the plan. So now we have multiple cells. In fact, if we go back one slide, you'll notice that we refer to this again as the Hadley cell. We still have our Hadley cell, but now it only extends from the equator up to 30 degrees north. Again, rising motion where we have low pressure at the surface, sinking motion where we have high pressure at the surface. And this cell, or this rotation, is going to help work with that. However, now we have what's known as the Ferrel cell, reversed, but still seeing sinking motion, where we have the subtropical highs, rising motion in this area of convergence near the polar front. And then we also have the polar cell. And so we have, again, rising motion near 60 north, and then sinking motion highs near the 2 poles. There would be an H down here if we drew an H by the southern, or the south pole as well. And so these cells, the Hadley, Ferrel, and polar cell, are also symmetric about the equator, and these help us to really describe some of these features that I've been spending time on, these ITCZ-like features, the subtropical highs, subpolar lows, and again, really helping us to understand why certain parts of the globe are commonly wet, such as the equatorial regions, and in fairness, we have areas near 30 degrees north and south that are contain some of the world's largest deserts, and we'll get a little bit more into that when we talk about climate late in the semester. Well, I'm pushing 12 minutes. Let's call this a video. We will start off with this slide again in class. Hopefully you have a chance to view the videos, and again, bring whatever questions you have to class, and enjoy your weekend.